Good evening, everyone. Welcome to Chem Help ASAP Wednesday evening live stream. I hope everyone is doing well. So, for this week, I thought we would work some different gas law problems. So, we'll do problems with Boyle's law and Charles's law and ideal gas law and just see a bunch of different kinds of problems and how we solve those problems. Okay, let's go ahead and get started. Okay, so for each of our problems, at least initially, I'm just going to keep all of the different gas laws over here in the top left-hand corner. And what I am noticing is that you guys cannot read the whole problem on the screen. So let me see if I can. It doesn't necessarily make that better, does it? Let me see if I can fix this by moving this problem down a little bit. There, that is much better. Now you guys can read the whole problem. Anyway, I'm going to have all of the gas laws right there so we can pick and choose what we need. And one thing that I find helpful as well is to have the conversions for the different types of pressures, because sometimes you need to convert and sometimes you do not need to convert. So I like to have all that information handy so that I can do the problems a little bit easier. Okay, now that we can read the problem without my face being in the way, let's go ahead and read our first problem. So it says a sample of ideal gas is placed in a piston. The initial volume of the piston is 1.5 liters and the initial pressure of the gas is 680 torr. If the piston is compressed to half its initial volume while the temperature is held constant, what is the new pressure of the gas? All right, so first we need to decide which gas law we're going to use, because I have 5 of them up here in the upper left hand corner and I need to choose which one I'm going to use. So when I look back at the problem, I'm just going to pick out what are my variables, what is changing, and what is not changing or what is being held constant. So I have an initial volume of 1.5 liters, and then I'm compressing to half that volume. So my volume is definitely changing. So I'm going to make sure that in my gas law, I have volume as a variable. The other thing that is changing is the pressure. So I'm initially at 680 torr, and I actually want to find the new pressure of the gas. So I need a gas law equation where volume and pressure are changing. And you can even see here temperature is being held constant. So as I look at my different gas laws, again, I want pressure and volume changing. Everything else is held constant, so I don't want those as variables. So Boyle's law is going to match this problem the best. So that is the gas law that we are going to use. Now that we know the gas law we're going to use, we can start actually doing the math. And sometimes I feel like deciding which gas law you're going to use is maybe the most difficult part of the problem, because if you don't know which equation to use, you don't even know how to start the calculation. All right, so before I plug into Boyle's law, I'm going to make a list of what I know and what I need to know. So I have an initial volume, or a V1, of 1.5 liters. I have an initial pressure. Oh, sorry, that should be P1, not P2. P1, and that is 680 torr. Okay, I have a V2, or a final volume. Now, the problem didn't actually give me the number, but it told me that the piston is compressed to half of its initial volume. So that is going to be 1.5 liters divided by 2, or 0.75 liters. And my pressure 2 is what the question is asking. So that is my variable. I'm just going to put a question mark here. That is what we want to determine. Now let's write down Boyle's law. So Boyle's law is simply pressure 1 times volume 1 equals pressure 2 times volume 2, and let's plug our numbers in. So our pressure 1 is 680 torr. Our volume 1 is 1.5 liters. Our pressure 2 is what we're looking for, so I'm just going to keep that as P2, and our volume 2 is 0.75 liters. Now, before I actually give the answer and go through the math, there is something I want to point out about these gas laws is you want to make sure that across the equal sign your units match. So see, I have liters here and liters here. It doesn't have to be liters. It could be milliliters. It could even be ounces or gallons, or however you want to measure volume. They just have to be the same. So the fact that I have liters and liters is good. That's what I want. That also means that my pressure here initially is in torr. So when I calculate my pressure 2, that is going to also come out as torr. Again, the units will match. So my P2, when I get that number, is going to be however many torr for the new pressure of the gas. All right, with that being said, when we plug into our calculators, we get a P2 of 1360. Again, that will be torr. So the actual calculation itself for this kind of problem is pretty easy, but again, deciding what equation you're going to use and making sure your units are matching across the equation, that's where I see a lot of students get tripped up with these kind of problems. Okay, no questions? So let's go ahead and go to the next question. Oh, and I'm going to have to move this one too, because it is, my face is blocking it. That looks a little bit better. All right. Again, I am keeping all of my equations here, and I've got my pressure conversions in case I need them. So let's read the problem. A sample of gas is placed in a sealed can. The pressure is initially 90,500 Pascal. The can is crushed but not broken. That is important. The system stays sealed to a volume of 375 milliliters. The pressure of the gas in the crushed can is 1.2 atmospheres. What was the volume of the can before it was crushed? All right, so again, we have to decide which equation we are going to use. So I want to know what variables are changing and what is being held constant. So again, I'm seeing pressure is definitely changing because initially I had 90,500 Pascal, and then after it's crushed, I have 1.2 atmospheres. So I definitely want an equation with pressure in it. And I'm also changing volume. I actually want to know the initial volume, and I have the final volume. So again, it's just pressure and volume that are changing. So that is going to be Boyle's law. So let's go ahead and write down Boyle's law. And I didn't list out what we know. So let's make sure we list out what we know. So pressure 1, let's maybe put this over here. So our initial pressure is 90,500 Pascal. My initial volume is what the question is asking, so I'm just going to write that as a question mark. That's what I'm going to try and find. My P2, or my final pressure, is 1.20 atmosphere, and my final volume, or my V2, is 375 milliliters. All right, so this is where it's important to remember that your units need to match across the equation. My volume isn't so much a problem because I will just get my V1 out in milliliters, but you can see my pressure 1 is in Pascal and my pressure 2 is in atmosphere. Now, it does not matter which one you convert. You can convert either one of them, but you just want to make sure they match. So I'm going to take my 1.2 atmosphere and I'm actually going to convert that into Pascal. And to do that, I'm going to use my conversion equations down here. So 1 atmosphere is going to equal 101,325 Pascal. I'm actually going to do this conversion equation kind of off to the side here. So I have my 1.20 atmosphere, and I want to convert that into Pascal. So in 1 atmosphere, I have 101,325 Pascal. That's kind of a wonky 5. So that will give me 121,590 Pascal. So now when I use that pressure, my pressure units will match when I plug it into Boyle's law. All right, let's plug our numbers in. I'm going to need a little bit of space because these pressure units are quite long. So my initial pressure again is 90,500 Pascal. My V1 is what I'm trying to find, so I leave that alone. My pressure 2 is 121,590 Pascal. And my volume 2 is 375, and that is milliliters. So now you can see my units are matching across the equation. I can solve for V1. And V1 is 504 milliliters. Again, I know it's going to come out in milliliters because I've got milliliters right here. All right. Any questions about this one? Okay, looks like we're pretty good. So let's go ahead and let's keep on chugging through all of these gas laws because there are quite a few of them. Okay, next problem, and I'm going to have to move it again. So all of these I'm just going to have to remember. Hopefully my moderator will help me remember if I forget to move these questions down so you guys can see them. Okay, so this question is a sample of gas is placed in a sealed container of, I think that's supposed to be of, not off, of adjustable volume. Initially, the canister has a volume of 2.75 liters and the pressure in the canister is 2.6 atmosphere. If we need the sample of gas to double its pressure, what volume should the canister be adjusted to? Okay. Again, I've got to decide which equation I'm going to use. So what is changing, what is not changing. So I have adjustable volume, so I definitely want volume, and I have a pressure of 2.6, and I want to double this pressure. So again, pressure and volume is changing, so I want Boyle's law. Just like before, I'm going to first write down what I know, and then I'll plug it into the equation. Okay, so I have initial volume. Here's initial pressure is 2.60 atmosphere, and my initial volume is 2.75 liters. And my pressure 2, again, it didn't give me a number, but it said that we want the pressure to double. So, sorry, that P didn't really work out. So my pressure 2, I want 2 times 2.60 atmosphere, which of course is 5.20 atmosphere. And for my V2 is what I want to find. Double in pressure, what should the volume? So that is my question mark. So I just go back and make sure I have everything I need. And now I can plug in to Boyle's law. So P1, V1 equals P2V2. So this is 2.6 atmosphere, and initial volume is 2.75 liters. My P2 is 5.20 atmosphere, and my V2 is what I am solving for. Again, I'm double checking to make sure my units match and everything looks good. And so my V2 is simply 1.38 liters. All right, so hopefully you're seeing that these are pretty easy kind of once you get the hang of them, once you get the hang of finding what's changing, what's not changing, and what your equations are, and then making sure your units match. These should start to move along pretty easily. Okay, any questions before I go? All right, just want to make sure there are no questions before I went on to the next one. Okay, and again, I still need to remember to move these questions down so that you guys can see them. That's better. Okay, a balloon is filled with a sample of gas. It occupies 35 liters at 15 degrees Celsius. If the temperature is lowered to negative 30 degrees Celsius, what happens to the volume of the balloon? All right, so I've got a new variable here. I have temperature. So what's going on is I have volume and temperature that are changing, and nothing else is changing. So I need a gas law where volume and temperature are changing. And if I look at all my gas laws, I can see that Charles's law is the gas law that I want in this case. So just like before when we did the Boyle's law problems, with the Charles law problems, let's write down what we know. Okay, so my initial volume, or my V1, is 35 liters. My temperature 1 is 15 degrees Celsius. My V2 is what I want to find, because what happens to the volume of the balloon? So that is a question. And my T2, I was lowered to negative 30 degrees Celsius. Okay, so this brings up something that we haven't run into with gas laws, and that is we cannot use Celsius when we use gas laws, because Celsius, we call this degrees Celsius. It's a relative scale. We need an absolute scale. So the only absolute temperature scale that we have is Kelvin. So we need to convert each of these temperatures to Kelvin. The good news is converting from Celsius to Kelvin, or even Kelvin to Celsius, is very easy. To convert from Celsius to Kelvin, we are simply going to add 273. So my T2, I'll do this actually in a different color. If I add 273 to this, sorry, this is T1. I said T2. My T1 ends up being 288 Kelvin. And I'm going to do the same thing here to T2, 273. And so my T2 is 243 Kelvin. Okay, so what you can see here is my T2 was a negative number. So hopefully if you had run into this problem and you plugged in a negative number, it wouldn't make sense, because you would get a volume out that was negative. And again, this is why we use an absolute temperature scale. You will never have a negative number in Kelvin, and you will also never have zero. So notice in Charles's law, you're dividing by temperature. So if you had a temperature of 0 degrees Celsius and you tried to plug that in, that is undefined. Again, this is why we go to an absolute temperature scale. All right, now we can plug in to Charles's law. So let's write Charles's law down. Equals V2 over T2, and we can plug in. Okay, so we have 35 liters over 288 Kelvin is equal to V2, which is what we're trying to find, over 243 Kelvin. Again, my units are matching. I've got Kelvin on both sides, and my V2 is going to come out in liters. So I can solve for V2, and I will get 29.5 liters. All right, let's make sure there are no questions. There are no questions. So that was a problem with Charles's law. Let's keep on chugging here. Let's go to our next one. And again, let me move this down so that you guys can read this. All right, great. Okay, a sample of gas initially occupies 450 milliliters. When the sample is heated to 110 degrees Celsius, the volume increases to 2.5 liters. What is the initial temperature of the sample? And the problem wants us to give us that temperature in Celsius. So we have to be a little bit careful. This problem is actually trying to trick us here. But let's write down what we know first, and then I'll show you how they're trying to get you to make a mistake. I have a volume and temperature here. So again, this is going to be Charles's law. So I have a volume 1 of 450 milliliters. I have a T1 of, I am not sure, that's what I'm trying to find, the initial temperature. So that is my question mark. My V2, or my final volume, is 2.50 liters, and my T2, or my final temperature, is 110 degrees Celsius. So there are a couple of tricks here. First, we need to take Celsius just like we did before and convert that to Kelvin. Again, that is very simple. We are just adding 273. And that is going to give us 383 Kelvin. Also, what we have is we have a unit mismatch. This is another place where the problem is trying to trick us. We have milliliters in V1 and liters in V2. Again, it doesn't matter if you convert the liters to milliliters or the milliliters to liters. They just have to match. I think I will convert this V1 to liters, so that would be 0.45 liters. I'll kind of squeeze that in there. And now we have units matched, and like Celsius, we converted that to Kelvin, which we always have to do in gas laws. And we're ready to write down Charles's law and plug what we know in. So we have V1 over T1 is equal to V2 over T2. So our V1, again, remember we converted to liters. And you will get the same answer if you convert this 250 liters to milliliters. Again, it doesn't matter. This is T1. That's what we're trying to find. And our V2 is 2.50 liters. And our T2 is 383 Kelvin. Again, making sure that our units match and we're converted to Kelvin. So when we do this calculation, we will get a T1 of 68.9 Kelvin. Now this is where this problem wants to trick you again, because I already wrote down that this was in Kelvin, and you think, oh, I solved for T1, I'm fine. But remember, the problem wants it in Celsius. So this could also be a situation where you see Celsius and you forget to convert T2 down here into Kelvin, but you keep it in Celsius. So just be careful about that. This problem really wants to make sure that you understand that you are converting into Kelvin, and then you solve, and then you take Kelvin here and convert it back to Celsius. All right, so to convert this back to Celsius, again, it's very easy. We're just going to subtract 273, which will give us negative 204.1 1 degrees Celsius. So that is the T1 that the problem wants. Okay, any questions? Nope, no questions? Then let's keep going to the next problem. And again, let me adjust this one down a bit. Okay. All right, let's read it. A movable piston initially has a volume of 150 milliliters and filled with a gas initially at 475 torr. If the piston is expanded to 500 milliliters, the pressure drops to 330 torr and the temperature of the gas becomes 48 degrees Celsius. What was the initial temperature of the gas? Okay, so now let's, again, just like before, let's figure out what our variables are, what's changing, what's not changing. So definitely we have volume that's changing. We have pressure that's changing, but we also actually have temperature that's changing too, because the problem actually wants us to calculate initial temperature. So we have 3 variables in this problem. We have volume is changing, pressure is changing, and temperature is changing. So if I'm looking at my gas laws over here, I need all 3 of those variables, which means I need the combined gas law in this case. All right, just like before, let's write down what we know. We just happen to have a lot more information in this problem. So we have our initial pressure is filled with gas at 475 torr. We have an initial volume of 150 milliliters. And our initial temperature is what we're going for, so that is our variable. That's what we're going to solve for. And our final pressure, our P2, drops to 330 torr. Our volume 2, piston is expanded to 500 milliliters. And our final temperature is 48 degrees Celsius. So the good news for this problem is our units are matching. That's great. We do need to convert this Celsius into Kelvin because we cannot do this problem without converting into Kelvin. So let's add 273, and this is 321 Kelvin. Okay, now we're ready to use our combined gas law. So combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. Now let's plug in. So we've got 475 torr times 150 milliliters over T1 is equal to 330 torr times 500 milliliters, and this is over 321K. Now, just algebraically, you can solve this several different ways, but when you're solving for a variable that's in the denominator, I do recommend cross multiplication as a great technique for that. Again, you don't have to do that. That is something that I usually use when I'm solving, again, for a variable that happens to be in the denominator. I like to use cross multiplication. But however you want to solve this algebraically, when we solve for T1, we get 152 Kelvin, which if we want to convert into Celsius, we are going to subtract 273, which would give us a T1 of negative 121 degrees Celsius. Oops, that's equals, and that is a negative. This problem didn't specifically ask for Celsius, but I thought I would just go ahead and throw it in there anyway. All right, before we move on, make sure there are no questions, and we don't have any questions. So let's go on to our next one, and again, let's get this in a place that you guys can read it. There we go. All right, we've got another balloon. You'll notice in gas laws there are a lot of pistons and balloons. So a balloon initially has a volume of 0.95 liters. It's at 850 torr and 20 degrees Celsius. If the balloon is released, it will expand to 1.35 liters and 7 degrees Celsius. What will the final pressure of the gas in the balloon be? All right, so we're also assuming that the balloon does not pop. Otherwise, the pressure would equal the pressure of the atmosphere. So let's figure out what's changing, what's not changing, which gas law we need to use. So we have volume here that's changing, we have temperature that's changing, and we have pressure that's changing because we want the final pressure. So again, we need something where volume, temperature, and pressure are changing. So that is again going to be our combined gas law. So let's go ahead and write down everything we know. So P1. There's our file. Okay, so P1 is 850 torr. Initial volume is 0.95 liters. And initial temperature is 20 degrees Celsius. All right. Our final pressure, our P2, is what we're trying to find, so that is our variable. Our V2, our final volume, is 1.35 liters. And our final temperature is 7 degrees Celsius. All right, so we do have units that are matching. However, just like before, Celsius does need to be converted into Kelvin. So let's go ahead and convert those into Kelvin. So we're going to add 273, and that is going to make T1 293 Kelvin. Again, we're going to add 273 here. And so our T2, is 280 Kelvin. Now we're ready to plug into combined gas law. So P1 V1 over T1 equals P2 V2 over T2. So let's get some numbers in here. We have 850 torr times 0.95 liters over 293 Kelvin. And this gives us whatever our pressure 2 is times 1.35 liters over 280 Kelvin. So solving for pressure 2, we are going to get 571 torr. And that is our final pressure in the balloon. Okay, any questions? Great, looks like we can keep on moving on. Okay, so once again, let me move this down so that everybody can see. All right, better. So this is a much shorter problem. It says how many moles of an ideal gas are present if the gas has a volume of 0.035 liters at 25 degrees Celsius and a pressure of 1.75 atmospheres. So reading this problem, you've probably already noticed right away this feels like a very different kind of problem. There's no initial final. There are not multiple pressures or volumes or temperature. We really just have a volume, a temperature, and a pressure. And also we are asked for moles, which is something we haven't been asked for. So we need an equation with all of these variables in it. So certainly Boyle's law and Charles's law is out. Combined gas law is out because it doesn't have moles. Possibly Avogadro's law because it has moles, and ideal gas law also has moles. So how do we decide between these two? Well, what I see is there are a couple things. I have a pressure, which Avogadro's law does not have, and I only have one volume. I don't have like an initial and a final volume. So again, this is not going to be Avogadro's law. We are now going to be working with ideal gas law. Now, when you're working with ideal gas law, just like we wanted the units to match across the equal sign for like Boyle's law, Charles's law, and combined gas law, we need to make sure that units are going to match with whatever value of R that we're going to use, or vice versa. You could say, I like to choose my R based on the units I'm given in the problem, but some people like to use the same value of R and then convert whatever values are given in the problem to that value of R that they prefer. But you can see R is right here, and this is 4 different values of R. There are so many more values of R, but these are the most common. And honestly, I would say this first one is absolutely the most common. You'll probably use that the most. But this value down here, this 62, this is a liter torr. You will also see this one pop up fairly frequently as well. These other two, again, you do see out there, but this is meters cubed and pressure in Pascal. So you see that a little less often. For our problem here, what we've got is we've got volume in liters and pressure in atmosphere. So I'm going to be inclined to use this value of R. Again, I like to take the units that I'm given in the problem and find a value of R that matches as closely as I can get it. And if I can get something that matches exactly, then that's the one I am definitely going to use. So I am going to be using this value of R for this problem. So let's go ahead and write down our ideal gas law. And let's go ahead and plug in what we know, and that should help us decide if we have enough information to proceed. So I do have a pressure, and that is 1.75 atmosphere. I was also given a volume, 0.035 liters. Now, N is my number of moles, which is what my problem asked for, so I'm going to leave that alone. R, again, I wanted to match my liters and atmosphere. So again, I'm using this first value for R. So that is 0.08206 liter atmosphere over mole K. And then my temperature here is 25 degrees Celsius. So hopefully you see the problem that I have already run into. But let's just go through and we'll find it. So units, atmosphere, good. Liter, great. Mole is going to be what N equals mole, but you can see I've got Kelvin here and Celsius here. Because remember, we cannot use Celsius when we use the gas law. We need to make sure we're using Kelvin because it is an absolute scale. So instead of using 25 degrees C, I need to convert that to Kelvin, so that is adding 273. I'm just going to squeeze in 298 K right there. So these are all the things that it's good to double check on before you start plugging things into your calculator, because it's very easy to start putting numbers in your calculator and just, I just want to finish this problem, get it over with. But really, we want to finish the problem correctly. All right, now I am ready to solve for N. So N is going to equal 0.0025 moles. Again, if you had put the 25 in there, I think you would have realized pretty quickly, wow, this is not really making sense. But it's always a good idea to check your units. I like to say, let your units lead you. If your units aren't matching or your units are not making sense, then probably something is wrong somewhere in the problem. Okay, so that was our first problem with ideal gas law. Let's make sure there are no questions, and there are no questions. Let's do a couple more of these because we've got time for that. All right, oops. Once again, let's move this down. Okay, what is the pressure of a 3.62 gram sample of oxygen gas? If it is at 15.5 degrees Celsius, occupies 27.8 milliliters, and behaves like an ideal gas. Okay, again, we're asked for pressure. We are given a temperature, we're given a volume, and we're given a mass, which is unusual. So let's first decide what equation we're going to use. Now, what I'm seeing here is, again, I'm not seeing like an initial position and then a final position, or an initial pressure or initial volume, final pressure, final volume. So I am not going to be using Boyle's, Charles's, Avogadro's, or combined gas law, which really just leaves ideal gas law left. And you're probably again saying, well, what about this gram sample? How does that factor in? Well, let's first go ahead, get ideal gas law in, and see what we can put in the equation, and then decide how we're going to proceed with this problem. Sometimes when, especially on a test, if I read a problem, I think I don't know how to solve it, but I think I can get the first step. Go ahead and write down the first step of that problem, because that'll often kind of get your brain going and you think, oh, that's right, I can connect these two IDs now. So for this one, I'm going to go ahead and write down the ideal gas law and then make a connection to make it work. So here is our ideal gas law, and let's fill in what we know. So we want to know the pressure. So we know that pressure is going to be our variable. We do have a volume. We've got 27.8 milliliters. Do we have a number of moles? No, we don't have a number of moles, so I'm just going to leave that alone. Do we have a value of R? Okay, so I have got temperature and volume, and I want the pressure. So let's go ahead and let's use our 0.08 value for R, and that'll give us our pressure in atmosphere. So let's go ahead and put that in. 8206, and that is liter atmosphere over mole K. And then we're given a temperature of 15.5 degrees Celsius. And I know you guys are already saying, Celsius, you need to convert to Kelvin. And yes, we do need to convert to Kelvin. But there's something else that I want to point out as well. So right now we have two variables, so we're going to need to figure out at least one of those. But I've got my Celsius, which needs to be converted to Kelvin, but also I have my volume in milliliters, and my R is telling me I need my volume in liters. So I actually have two different conversions to make. I've got to change this milliliters and that Celsius. Okay, so that's really not that big of a deal. I can do the conversion on that. But how can I get either N or pressure? And so as I go back and read the problem, I see that it asks me what the pressure is. So that makes me pretty certain that pressure is supposed to be my variable, which means there should be a way that I should be able to figure out N, or the number of moles. Again, I go back to the problem, and I have not used my mass yet. So I have 3.62 grams. Is there any way I can turn that grams into moles? Well, yes, I can, because I know that this is a sample of oxygen gas, which means I know the molar mass, so I can convert this 3.62 grams into moles using the molar mass. So let's go ahead and do these conversions. I'm going to first do the grams to moles. So maybe I'll do this in green because it's a little separate step. So 3.62 grams of oxygen. Again, using the molar mass of oxygen, 31.9988 grams of oxygen in 1 mole of oxygen, and that gives me 0.113 moles of oxygen. My 15.5 degrees Celsius plus 273 is going to give me 288.5 Kelvin. And of course, my 27.8 milliliters is the same as 0.0278 liters. So those are all the conversions, and I had to do a lot of conversions for this problem. And now I'm ready to basically plug back into ideal gas law, and I should be able to get the pressure out now. So I still have P for pressure because that's what I'm solving. My volume is now 0.0278 liters. I know my number of moles is 0.113 moles of oxygen. My R is staying the same. Whoops. I started to write 8 there. 0.8206 over mole K. I'm going to try and squeeze my temperature in to 88.5. That's a little squash. That is my 288.5 Kelvin. All right, so just double checking, making sure all my units are matching up. I have liters, and I have liters, and I have Kelvin, and that is Kelvin over there. I have moles, and I have calculated my moles of oxygen. Now, when I calculate my pressure, the pressure is going to come out in atmospheres because that is the unit that I used. So my pressure is 96.3 atmospheres. That is some high pressure gas right there. So anyway, hopefully this kind of problem shows you, even if you don't see your way to the end of the problem, just take the first step. And often that will lead you to the next step. And again, you can kind of snowball and get your brain going and go, oh, wait, I think I can go ahead and solve this problem. But it's always okay to look at a problem and say, well, I know the first step, but I don't know how I'm going to get to the end. That happens to everyone. Okay, let's make sure we don't have any questions. We don't have any questions. And I think we've got time for a couple more problems, I hope. All right. Oh, once again, this one actually is, maybe I'll move it a smidge over here. But this one I have not blocked, so good. All right. A 0.063 gram sample of unknown ideal gas has a pressure of 855 torr, a volume of 355 milliliters, and we are at 35 degrees Celsius. What is the molar mass of the unknown sample? And based on the molar mass, what is the identity of the unknown? All right, so we know we're dealing with ideal gas law here because, again, we don't have an initial situation and a final situation. And honestly, the problems that we get to from here on out are going to use the ideal gas law. So let's just go ahead and write ideal gas law down. PV equals nRT. And again, this is an easy one to say. Ideal gas law doesn't have grams in it. How are you going to get molar mass out of this? This doesn't make sense. And there are two ways that you can go about this problem. So we can go about it using ideal gas law, or there is an equation that you can use to get molar mass out of ideal gas law, and it is PV equals the mass of the sample over the molar mass times RT. Now, if you have access to this equation or you have it memorized, you can absolutely use it. But sometimes you're on a test and maybe you have tried to memorize it, but you have forgotten it in kind of the panic of the test. So I am going to go through this problem and I am only going to use the ideal gas law to get to the answer of this problem, because you can use either, but I want to show how, again, you can use ideal gas law for this particular problem. All right, so we know that we are going to have to do some conversions here, right? We certainly are going to have to change this 35 degrees Celsius into Kelvin, so let's go ahead and do that. I'm actually going to squeeze this over here. So 35 degrees Celsius, again, we add 273, and we're going to get 308 Kelvin. Also, if I look at my values for R, I have either liters or meter cubed for my volume. And here I've got milliliters. Again, you can find an R that has milliliters as its units, but I'm going to stick with these values of R I have right here. So I am going to go ahead and convert that milliliters into liters. So 355 milliliters is the same as 0.355 liters. All right, so I think our units are going to work now with our ideal gas law. Because I have a pressure of torr, I'm going to use this 62.3 value for R. Again, I like to take what I have and try to do as few conversions as possible and then find an R that matches that. So let's go ahead and plug in what we know. Okay, so we have a pressure of 855 torr. We have a volume of 355 liters. We do not know our value of N, so I'm just going to leave that as N. Because I have torrs and liters, again, I'm using a different value for R here. I'm using 62.364 liter torr over mole K. And of course, my temperature I did convert, that is 308 Kelvin. All right, so just to make sure my units are matching, torr and torr, liters and liters, mole, which is going to be N, and K here. All right, so looking at what I wrote down, I can solve for N. So even though that's not what the problem has asked for, let's go ahead and get our number of moles, because we've plugged everything in and we can calculate our number of moles. So for this problem, our number of moles is 0.0158 moles. Now my question is, do we know what this gas is? And no, we have an unknown ideal gas law, and actually we want to find the identity of that. So I can't take these grams and then convert to moles because I don't have a molar mass. I don't know what the identity of this sample is. So now what I have is I have the number of moles and I also have the grams. So if I'm thinking about molar mass and I think about the units of molar mass, it's always grams per mole. So I can calculate the molar mass by taking the grams of the sample over the number of moles, and that should give me the molar mass. So I have grams because the problem gave me grams. So that is my grams of my unknown. And I just calculated moles from ideal gas law. So here are my moles. And that gives me a molar mass of 4.006 grams per mole. So now I have the molar mass. All I need to do is identify this unknown. And if you go look at the periodic table, you can see that helium has a mass of about 4. So this ideal gas is helium. Again, you can use this equation, and that is 100% perfectly fine. You will get this answer out. But if you're ever stuck on a test, know that you can use the ideal gas law, and you just kind of have to work through the problem, collect the information that you know. Again, in this case, we could solve for n, so I went ahead and solved for the number of moles, even though I wasn't 100% clear how I was going to get to the last step. And then you just needed to put this final piece together to say, wait, I need molar mass. Molar mass is grams per mole. I have grams and I have moles. I can divide and find the molar mass. And a lot of times that, at least for me, is how I worked through problems on tests or in homeworks as well. And I can see that we are actually at 8 o'clock right now, so I will not be able to get to the other problems that we had planned, but I had more problems like this. So if you would like to see some more gas law problems, especially with ideal gas law and dealing with other problems with molar mass and with density, you can always email me and let me know. Or if you'd like a completely different topic next week, that's perfectly fine. Again, just email me and let me know. But thank you so much for joining us tonight, and I hope to see you next week. Bye.